let's suppose that you want to observe three different reactions in three containers A, B, and C. Container A contains a mixture of nitrogen and hydrogen gases that are reacting together. Container B contains only ammonia that is decomposing. And container C contains both, a mixture of nitrogen and hydrogen reacting together and ammonia that is decomposing. Which of the three reactions will reach equilibrium? What are the necessary conditions for reaching equilibrium? In this video, we will discuss how to determine if a reaction has reached equilibrium. We will also discuss why different conditions, such as temperature, pressure, volume, and containers, must meet specific criteria for a reaction to reach and maintain equilibrium. We can tell whether the reaction has reached equilibrium or not by looking at the concentrations of all substances at regular intervals as the reaction proceeds. For example, let's look at the three reactions in containers A, B, and C that we introduced earlier. If we focus on the reaction in container A, which contains a mixture of nitrogen and hydrogen gases, we notice that initially nitrogen and hydrogen react together to form ammonia. The rate of forward reaction is higher as the number of molecules of ammonia produced keeps increasing. However, after some time, molecules of ammonia that were formed start reacting together and decomposing into molecules of nitrogen and hydrogen. Now, the rate of reverse reaction starts to rise. After a while, we notice that the concentrations of all substances have stopped changing. At that point, there are 4 moles of ammonia, 9 moles of hydrogen, and 3 moles of nitrogen in the reaction. The number of moles is not changing anymore. This means that the rate of forward reaction has become equal to the rate of reverse reaction. In other words, the rate at which nitrogen and hydrogen are reacting together to form ammonia is equal to the rate at which molecules of ammonia are decomposing back into nitrogen and hydrogen. Because of these equal rates of forward and reverse reactions, the concentrations of all substances have become constant. Therefore, the reaction reaches equilibrium when the concentrations of the substances stop changing. They become constant. Will the reactions in containers B and C also reach equilibrium? Yes! Initially, container B contains ammonia only. Therefore, in the beginning, we only see ammonia decomposing into hydrogen and nitrogen. However, as more and more molecules of nitrogen and hydrogen form, they react together, forming ammonia again. This process continues until the concentrations of all substances become constant, as we saw in container A. Similarly, container C contains a mixture of nitrogen, hydrogen, and ammonia. After a while, the concentrations of all substances become constant as the rates of forward and reverse reactions become equal. Therefore, even though all three reactions are the same reversible reactions, equilibrium can be reached if the reaction contains reactants only, products only, or a mixture of both reactants and products. However, there are certain conditions that also must be met. What happens if we change the temperature during a reaction? Will the reaction reach equilibrium faster, slower, or not at all? It depends on the type of reaction. Some reactions, such as the reaction of nitrogen and hydrogen to form ammonia, require a lot of heat. Other reactions, however, happen spontaneously and release heat as they occur. For example, the reaction of sodium and water to form sodium hydroxide and hydrogen gas is highly explosive. Reactions that require heat to take place are called endothermic reactions. However, reactions that occur spontaneously and release heat are called exothermic reactions. Increasing the temperature increases the rate of endothermic reactions, but decreases the rate of exothermic reactions and vice versa. Therefore, to maintain equilibrium, the temperature must be kept constant. In a closed container, we can also change the pressure by varying the volume of the reaction vessel and keeping the temperature constant. When the volume of the container is reduced, molecules collide with each other and the walls of the reaction vessel. This increases the pressure. Conversely, increasing the volume of a closed container at a constant temperature reduces the pressure of the system. Therefore, for a closed container, increasing the volume decreases the pressure, and decreasing the volume increases the pressure. When the pressure of a system is increased, the reaction produces fewer moles. For example, in this reaction, the reactants contain 4 moles in total, 1 mole of nitrogen and 3 moles of hydrogen. However, the products contain only 2 moles of ammonia. When pressure is increased, the position of equilibrium shifts in a direction that favors the formation of fewer moles in order to reduce the pressure. Therefore, in this example, an increase in pressure will favor the formation of the product, ammonia. This is because the product has only 2 moles and the reactants have 4 moles. Conversely, when pressure is decreased, the position of equilibrium shifts in a direction that favors the formation of more moles in order to increase the pressure again. Therefore, in this example, a decrease in pressure will increase the formation of reactants. Thus, in order to maintain the equilibrium, both pressure and volume must be kept constant. Finally, we will look at how open and closed containers affect equilibrium. When a container is open, the molecules of both the reactants and the products can escape. The rate of forward and reverse reactions will never become equal. However, when a container is closed, both reactants and products are trapped inside. Therefore, reactants can react together to form products, and products can react together to form reactants. Hence, to reach equilibrium, the reaction must occur in a closed container. Here's what we learned in this video. A reaction reaches equilibrium when the concentrations of all substances in the reaction become constant. Increasing the temperature increases the rate of endothermic reactions and decreases the rate of exothermic reactions, and vice versa. Therefore, the temperature must be kept constant for a reaction to reach equilibrium. Increasing the pressure shifts the equilibrium in a direction that favors the formation of fewer moles and vice versa. Therefore, pressure and volume must be kept constant to maintain an equilibrium. Equilibrium is only reached when a reaction happens in a closed container or an isolated system of a fixed volume at a constant temperature and pressure.